So there are a lot of different metrics and whatnot that we can consider for two sample, but we are going to deal with the three that pop up the most and the ones that are most relevant. Two proportions, so two samples, two proportions, matched samples, and two samples for t-test. When we do the two sample for t-test, we will assume that they have equal variance. We're not going to worry about unequal variance. Now, the textbook does cover unequal variance. If you're interested in that, you can look at it. But as a practical matter, when we're comparing two samples, what we're pretty much always checking for is, are they different? If they have unequal variances and their standard deviations are different, by definition, the sample is different. That's trivial. So if we did a test with unequal variance, we're assuming they're different. So we'll take the most restrictive approach and assume that the standard deviations are the same. Because the standard deviations are the same, or basically equal variances, then we can specifically check to see if the means are different. And oftentimes that's what's most important. But for now, we'll start with the proportions. And this is already here in case you haven't started writing it down. We stay with the normal distribution. And on the exam, you'll be asked to explain why you have the normal distribution of t-distribution. For t-distribution, it's because you don't know the population standard deviation. When we're dealing with just when you know the population standard deviation, that's trivial. But in this case, for proportions, what you're going to want to do is say this. The standard deviation for a proportion is based off of the proportion itself. The reason why we use a t-distribution is because we have to use some of our sample approximating our standard deviation. But when we're dealing with proportions, the proportion itself gives us the standard deviation. And this is why when we're dealing with proportions, we get to use the normal distribution. In this case, we have two samples, let's say sample 1 and sample 2. So P1 bar is just the proportion from the first sample. P2 bar is the proportion from the second example. This P bar is what happens when we pool the samples together. And they call it a pooled estimate. This is really just the average of the samples. It's a weighted average of the sample to be precise. Technically, if you wanted to put this in the weighted average formula you're familiar with, this would be the same as N1 over N1 plus N2 times P1 bar plus N2 over N1 plus N2 P2 bar, where the weights would be N1 over N1 plus N2 and N2 over N1 plus N2. And that makes it much more clear why it's pooled, it's weighted. And obviously, if one of the samples is bigger than the other one, then it has more weight because it's a bigger sample. Now, in this case, we will pretty much always deal with two-tailed because all we care about is, are they different? And when we deal with two-tailed, we have probabilities from both ends. So we have half a probability on each end, so that makes it more restrictive. So in this case, for the approaches we'll be doing, we might cover a couple of one-tailed ones, but as a practical matter, we're going to be mainly considering if they're different. Here's why. Let's suppose we do the two-tailed and we prove they're different. Well, we know which way they're going to be different because one's going to be bigger or smaller than the other one. So if we're comparing grades from two classes and we prove they're different, whoever's got the higher grades, that's the direction it's in. So that makes it pretty trivial. And I think it's easier to stick with stuff that's more restrictive, but also makes the interpretations easier. So our p-value will be 2 times the probability of z being less than the negative of the test statistic. For those of you who recall from the previous lecture, the reason why we take the negative of the absolute value is because that means you don't have to worry about the complement law and means you only need half of the z tables. Our critical value will be our z-score that satisfies alpha over 2 is equal to p of z being less than the critical value. Again, you do that from a reverse table lookup. You should take your alpha, you divide it by 2, say you had an alpha of 0.05. Divide that by 2, you get 0.025, and then look for 0.025 in your z tables. The z-score corresponding to that is your critical value. So does anyone need more time to write this down? And remember, if you're at home, you can always use the snipping tool. I have it right here, but you can just go type in snipping tool. You can take that. You can snip it like this, so that way you can have it by your side, make it nice and easy. So here, for each of these, I'll do one example, and then y'all will do one on your own, so it's going to get repetitive really quickly, and many of these concepts basically came up on the previous one. You'll notice this one right here, the only difference between this and the previous was that instead of just dividing by the square root of n, we technically have 1 over n1 plus 1 over n2. That's the main difference. Other than that, it's largely the same. All right, if you're at home, go ahead and snip it. Otherwise, we're going to move on to our example. So here, let's suppose we have these two poles of Wisconsin, sample size 1,000 each. And we want to conduct a hypothesis test of whether or not the poles are significantly different. State our hypotheses, alpha, and the conclusions of p-value approach. That A you see right there, that's pretty much going to be the exact same wording as the exam. You might have different values. It might be a different hypothesis test, but it's going to be worded the exact same. You're going to have to give your hypotheses. You're going to have to state your value of alpha. You're going to get your test statistic. And you're going to get your conclusion. So the first thing we have to do is get our two hypotheses. So we're trying to see whether or not the poles are significantly different. Doesn't matter what direction, as long as they're different. So we know we're going to have a not equal to and an equal to. The equal sign always has to go with the null. So we're going to have P1 is equal to P2. And then P1 is not equal to P2. Now we need our value of alpha. This is equal to 1 minus the confidence level rho, which is 95%. So 1 minus 0.95. So 0.05. Now, we need to weigh the poles together. A nice shortcut, if the two samples are the exact same size, then they have the same weights, and therefore, the pool is just going to be the halfway point between the two. So in this case, I can already tell you, 51%, 57, it's going to be 54. But let's use the formula anyways. So we have our first sample size of 1,000. And then we have 51%. Our other sample size is also 1,000, and now it's 57%. And then we have to add our two sample sizes together, so 1,000 plus 1,000. Let me pull up a calculator. 51% of 1,000, that should be 510. Other one will be 570. 1,000 plus 1,000 is 2,000. 54%, which is what the heuristic gives. So if your sample sizes are the same, you should take the halfway point between the two. Nice and easy shortcut. So this is 0.54, which is our pooled p-bar. Now we can get our test statistic, and your test statistic never depends on the value of alpha. Doesn't matter what alpha you pick, test statistic is always going to be the same if your other data does not change. So here we recall, we first have P1 bar minus P2 bar. In this case, we could do the negative or we can do the positive, because if we do P1 first, then we're going to have negative 6%. We do P2 first, we'll have positive 6%. Doesn't matter which one we take. So let's just stick with the first one. So we have 0.51 minus 0.57. And our denominator, we have our P bar times 1 minus P bar. So 0.54 times 1 minus 0.54. Let me make this square root a bit bigger. And now 1 over n1, which is 1,000, plus 1 over n2, which is also 1,000. We can put this straight into Desmos. You can have Desmos simplify this for you to the decimal. Just let me know. This is your z-score. So let's go ahead and pull it up. 0.51 minus 0.57 over the square root of 0.54 times 1 minus 0.54, and then 1 over 1,000 plus 1 over 1,000. Negative 2.692. So for credit, you have to write down what's here. Technically, you can just say alpha is 0.05. That's just literally mental math right there. That's just identification. The rest of these you'd want to write down. All right, now we want to get our p-value from this. We're looking for negative 2.69. That's negative 2.6. And then the 0.9. So that is 0.0036. And so therefore we have a p-value of 0.0036. If you want to round that, you could say 0.004. That is well below our value of alpha. Now keep in mind though, you have to take alpha over 2 because it's two-tailed. So technically we have to take alpha over 2 is 0.025. No, this is our actual test statistic. We have the difference of our two, so we have the 0.51 and the 0.57. And then here we had 0.54 times 1 minus 0.54. And the 2 1 over thousands. Now our conclusion, the poles are significantly different. So if you wanted to write this down, you would say that, well, actually, I just said that part. Since the p-value of 0.0036, you can put that or 0.004, I'd take either, is below the cutoff of 0.025. If you put 0.05, that'd be wrong. Yes. Pardon? Yes, doesn't change. Yes, you're correct. Sorry, I forgot about that. Forgot it was two-tailed, got to multiply from both ends. But actually, fun fact that you point that up. If we divide alpha by 2, that's the same as multiplying the p-value by 2. The cutoffs change both ways. So actually both are correct. So this one would be correct, or we could multiply this p-value by 2 and get 0.0072 and then compare that to 0.05. Both of those are correct. You can deal with either of them. Thank you for pointing that out. So I'll put in parentheses or 0.0072 below 0.05. Both those will work. We reject the null that the poles came. Let me scroll down to give us some more space. That the poles came from the same population and that they are equal. So in this case, these two poles are too different for this to have happened by random chance. So therefore, we can say one of them is dead wrong. And as you all know from the election, Wisconsin was pretty close. So the second poll, 57%, was dead wrong. That was an actual poll, and it was completely screwed up. And the issue with that poll was, once again, it undersampled the non-college educated whites by too much. Now, it is possible for the second one to be dead wrong and neither be significantly different. One way to do that is to significantly lower the sample size. For example, notice if we lower this to 250, that z-score doesn't cut it. Yes. Pardon? So if it's not equal to, it's two-tailed. If you have the greater than or less than sign in your alternative, then it's going to be one-tailed. Sorry, that should be, take off the 0. That's going to be nowhere close. Let's suppose we had sample sizes of 500. Doesn't quite cut it. So this is why with the polls, they have to have a pretty big sample size to get that margin of error small enough. On the other hand, let's suppose that our second poll was 54%. That still would have been completely screwed up. That's nowhere close because that would have had Biden winning by 8. He won it by less than 1. But if it was 54%, then this would be our new z-score. Doesn't cut it. The reason why this happens is not really because of this term, it's because of this term. As y'all will recall, let's say we have some x and then 1 minus x. That's the square root because we already have that. You'll notice it's maximized around 0.5. And if we're close to 0.5, say 0.46 or 0.54, it's still basically 0.25. This is the issue a lot of pollsters run into. They don't take this into account. And so they get a result with Biden winning Wisconsin by 54%. Well, 54%, they're like, oh, this seems right. And it's because of this. Any questions before we move on to the practice one? Okay. I will give you a moment to do this one. It's kind of obvious what your conclusion will be, but go ahead and do it. Now, as a little note, if your z-scores are further away than -3 or +3, your p-value is basically 0. Technically, from -3 to -7 and +3 to +7, you technically have a p-value, but it's very low orders of magnitude. Fun fact, once you get past +7 or you get below -7, the p-value is literally 0. So just as an example on that, on the assessment number 2, the average was around a 75. The standard deviation was a 10. So if you had a z-score of 7, then that would mean you were 70 points above a 75. That's after the curve. That means you got 145. Bullshit. Not possible. Now, of course, if you had a z-score of 5, that's pretty much equally ridiculous, and you'd still reject on that. But just as a fun little note, if you're between -3 and -7, or +3 and +7 for a z-score, or t-score for that matter, technically the p-value exists, but it's so small that you're pretty much rejecting no matter what. If your z-score is above 7 or below -7, it just doesn't, it's impossible, literally impossible. You could take every single human on the planet and have them do that for the rest of their lives, still wouldn't happen. Anyways, I'll give you a couple minutes to work on this. Does anyone need more time? Does anyone at home need more time? Okay. Then let's go over it. First of all, we have to get our hypotheses. They're actually going to be the exact same as before because we're just trying to see whether or not they're different. So we're going to have P1 is equal to P2. P1 is not equal to P2. We have 85% confidence. So alpha is 0.15. And now we have to pull these together. Again, we're going to use the shortcut from before. They both have sample sizes of 4,000. So it's going to be the halfway point between the two. Halfway between 51 and 39 gives a p-bar of 45%. Same method as before, we get to use a shortcut. If you want to keep plugging it into the formula, that's fine. It's up to you. Now our z-score, we can go from either perspective, doesn't matter, let's do the positive this time. So first one is 0.51. Our second one is 0.39. And as a note, on the WebWorks, it will tell you which one to let be 1 and which one to be 2. P1 is equal to P2. Are you talking about the p-bar? The p-bar is 45%. And now we have the square root of our 0.45 times 1 minus 0.45. And now we have 1 over 4,000. It's going to be a pretty low z-score. That's a 0. That's supposed to be 4,000. So now we'll put this into our Desmos. So 0.51 minus 0.39. Now we have 0.45. 0.45. You see this z-score is getting off into nowhere, which is good. So that's an example I wanted to talk about. This isn't on your table. Like I said, if it's outside of the 7 range, it's literally 0. So whether or not we double this p-value doesn't matter. Whatever confidence level we picked didn't matter. So in this case, we're going to have, I'm just going to put greater than 10. That lagged a little bit. So p-value is pretty much literally 0. So no matter what you're rejecting, so we reject the null that the two poles came from the same population. So one of them is clearly screwed up. It's pretty obvious which one is screwed up. But again, notice we had to have one of the poles be really, really screwed up to get a p-value that low. And as I discussed before, the reason why is because anytime we're around 0.5, that square root becomes maximized. This is why when you do the polls, you have to have sample sizes in the thousands. Like for example, Pew Research, they go into the tens of thousands. And just as a case in point, with Pew, they have sample sizes in the tens of thousands. So, for example, Pew, they do these polls over time. Let's say they had one from 2 years ago and they had one from now, and they're testing support for abortion. And in the past, it was, say, 0.55, and now let's say it's 0.57. Might look like a small difference. You pull them together, that'll be 0.56. But now it works. The reason why is because they have the sample size that big. So in general, this is why Pew very rarely runs into issues, because their sample sizes are big enough that even if their results are close to 0.5, they'll still get a pretty solid score if they're well different. And this doesn't only just poll proportions, it can be error rates. Like say you're dealing with the probability of an accountant screwing up. Now, let's say the chances of an accountant screwing up are say 5% versus 7%. Because this is way out on the tails, you can see it's way steeper. With around 5%, that's about 0.2179. With 7%, that's about 0.255. And with the square root, that matters a lot. So when you get out on the lower ends, your sample size doesn't have to be as big. Anyways, let's move on. Now we have something called matched samples, and we'll have a little bit of a throwback to chapter 3 here. I said this all builds on itself, and you'll see why. With this one, there's much more formal definitions. The easy one is you have one person, they take two different tests, and that test can be whatever you want. It can be literally a test, say like the assessment number 2. Or the great example, the midterm exam number 1. You took the old one, then you took the retake. You're the same person taking two different tests, so I can directly compare the scores that way. Another one, you can have an employee, and let's say they're operating two different machines, and you can get how quickly they're able to operate with each of them. That's why test is in quotations. And when I say, it could be a group, it could be 5 people doing it together, doesn't matter. Just as long as you have one person doing 2 tests. Test can be whatever you want. Now, what matters here is the difference between their 2 results. So it says denote each, it could be person, it could be the group or the entity, doesn't matter. We go from 1 to n. You might say, why don't we go from 0 to n? Because then you have n minus 1 people. We can keep it easy and stick with n. Then each difference, we have n differences. And these differences is literally the difference between their 2 results. So if you had a 75 on the old midterm exam number 1, and you had an 85 on the retake, then your DI would be 10. And we calculate that DI for everyone. And now we have our sample, and we can get our sample mean, sample variance from those. Now, I use sample variance instead of sample standard deviation. And the reason why is because when calculating your t-score, it makes the formula a little bit easier to work with. Instead of having to take the square root twice, you can do it once, saves you a little bit of time. Now, you will recall these 2. This is the same from chapter 3. You should use it all over again. Now, these differences, you'll have to calculate them on your own. You can have a computer do them, but the web work examples, which I will show you in a moment, you can do mental math. You don't need a calculator for it. Now here, when we're doing these tests, we do care about the direction. So sometimes we just want to see if they're different. Other times we want to see which direction they're different. Now here we're going to have t-scores. And the reason why we have t-scores is because we calculate the sample variance. We're using the sample variance to approximate all of the variance of all of the possible results they could have had. So that means we have to use a t-distribution. Other than that, these two, same directions that you saw from chapter 9. Now, technically, since this is a new type of sample, we have the confidence interval here as well. But you'll notice all of these depend on getting your S squared. The D bar is pretty straightforward. You just average all the differences. That should be very trivial. Sample variance, you're going to want to use the method that we talked about with the tables all the way back in chapter 3, which I will use here. Your degrees of freedom is just n-1, like with before. And the test statistic is the same formatting as before. The only difference is instead of having the sample standard deviation S over the square root of n, now I have S squared over n, square root the whole thing. It makes your calculations a little bit easier. So I'll give you a second if you need to write this down. That confidence interval, this T of alpha over 2, it's the same notation as before. And you'll notice this confidence interval doesn't matter if we're dealing with one-tailed or two-tailed. Confidence interval always wants T of alpha over 2 or Z of alpha over 2. Because we're going out in both directions. If you're going out in both directions, we're trying to maximize the data we capture while minimizing the distance. That's by using the alpha over 2. Yes, that's mu of the differences. So this mu d, you're given it in the problem. So for example, where? This is alpha. This is alpha over 2. Anyways, I forgot what I was saying. Oh, this mu d, you're given it in the problem. So for example, usually this mu d will be 0. So we're trying to see whether or not they're different. Sometimes you want to see how significantly different. So for example, you might know they're different, but you want to get a lower bound on how different they are. But the mu d will come from your hypothesis test. Usually it'll be 0, not always. I know it's a lot of writing, so I'll give you an extra minute to write it down. And if you're dealing with a one-tailed, be careful with your critical value. It can be positive or negative depending on your sign. And for two-tailed, your critical values are from two ends because you can reject either on the far negative end or the far positive end. So in that case, you just take both. All right, does anyone need more time to write this down, either in person or at home? If you're at home, you can snip it and have it next to you so you can write down for later, or at least reference. And I will note, I wrote a lot of this down already on here. This little part right here, I didn't write it down on the sheet. And the reason why is because this is the exact same directions as with the one sample t-test. So you want to save yourself some space on your cheat sheet, that's one good way to do it. All right, let's go to our example. 10 people do an IQ test. We have their scores, and we want to see whether or not they do better on one than the other. So before we can even do the test, we have to get our data. So we need our differences. So I'm going to make this text. Here, let me zoom in, make it easier. That's too big. Let's make that smaller. There we go. Let's make this maybe sample size 10. This will be all differences. 94 minus 94 is 0. Notice it's saying test A minus test B, so top minus bottom. Like I said, it'll tell you which order to do these things. Next one, 96 minus 96 is 0. 101 minus 99 is 2. 126 and 129, that's -3. Keep your signs. 112 minus 110, that's 2. 74 and 73, that's 1. 85 and 86, that's -1. 104, 102 is 2. 92, 93, -1. And our last one is -4. Don't worry about the spacing as long as you see the 10 numbers. Now we need to average those together. So 0, 0, 2, -3, 2, 1, -1, 2, -1, -4. Divide that by 10. Our D bar is -0.2. So D bar is -0.2. Now we need the variances, and now we're going to have to use the good old table from before. So we're going to put, and don't put the values, put the differences. If you put the values, you screwed up. So I'm just going to type these in, make it a little bit easier. Oh, come on. There we go. So our values, Let me go back to the standard font size. We had 0, 0, 2, -3, 2, 1, -1, 2, -1, and -4. And we need to get the squares of the differences. So di minus d bar squared. So here, this will be 0 minus -0.2. So that's the same as plus 0.2. And then we square that. This one's the same thing. So that's since we have minus and negative, these are all going to be plus 0.2s. And now we have 2 plus 0.2, -3 plus 0.2, and blah, 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 blah. I will just write it out because I'm 90% sure that everyone here can read. Unless someone raises their hand, I can make that 100% confident. Almost there. And -4 plus 0.2 squared. So now let me draw the equal signs. This is the most tedious part. Once you're past this, you're back to the standard hypothesis test. 0 plus 0.2, that's just 0.2. We square that. 0.04, we have that twice. Because the one below it is also 0. Now we do the 2. 2 plus 0.2, square that. 4.84, we have 3 other 2's. So we can save ourselves some time and bring that down. Another 2 right here. We have one more down here. Next one, we have -3 plus 0.2, square that. 7.84. Now we have 1, 1. 1 plus 0.2, square that. I believe that's 1.44. Yes, it is. Now we have -1 plus 0.2. It's -0.8, square that, 0.64. And we can write that down twice. And our last one is -4. Square that, 14.44. Now we add these all together. Because we sum up the differences. If you divide by n, you screwed up already. It's a sample standard deviation. So you have to divide by n minus 1. So now let's add all these together. 0.04, 0.04, 4.84, 7.84, 4.84, 1.44, 0.64, 4.64, 14.44, 39.6. Now we divide this by n minus 1. We have 10 of these. So 10 minus 1. Ah, that's very nice. Don't have to worry about rounding. 4.4. So now we have our sample variance. We can finally move the hell on. Now we can do the test. So here we're trying to see if people do better on the second. That's greater than, so we can say that. So now these are the differences, something you have to be careful of. We're dealing with the differences. This is mu d, we might call it. So we're dealing with mu d, so let's write that down first. So this difference is a minus b. So if they do better on the second, then this mu d has to be negative. Because if they're doing better on the second, then b is greater than a, so a minus b has to be negative. So therefore, this is less than 0. The null is the opposite of the alternative. So then this would be greater than or equal to 0. This is matched pairs, because I said so. Well, as a practical matter, quite literally says they take the easy shortcut. If you got one person taking 2 tests or whatever that test might be, that's your key to it being matched pairs. Our value of alpha is right here. Now we can get our test statistic. It's T is D bar minus mu D over square root of S squared over N, but we have to get our degrees of freedom first. Our degrees of freedom is 10 minus 1, so 9. And our T score, which is our test statistic, D bar minus mu D, so negative 0.2, minus mu D, which is 0. And now we have the square root of S squared over N. So the square root of 4.4. Don't square that 0.4 for 4.4, because then you have S to the power of 4. Over 10. I will just put this into Desmos. Negative 0.2 over the square root of 4.4 over 10. That is a test statistic of negative 0.302. So if you put that into here, that'll work. Now, our critical value, this is one-tailed, so we're just looking for 0.01. Because the 4.4 is already squared. You recall this 4.4 is S squared. So that's the variance. We don't need to square it again because this is S squared and it comes down into there. All right, so now we need to get our critical value. That is 0.01. And this one we'll use the critical value approach because that tends to be easier for matched pairs. So now we have 9 degrees of freedom. So our critical value, and I'll draw an arrow. That's the positive though. So we have to take the negative of it because remember, if we're dealing with the left-hand side, we got negative. So 2.821, this is negative 2.821. Don't forget about your sign. If you're doing these tests and your critical value is wrong, the first thing you should do is change the sign because you might have screwed up there. In this case, there is nowhere close to sufficient evidence. Our t-score is nearly 0. So no, because our 0.302, because remember we take the absolute value here for comparison to make it easier. 0.302 is less than the 2.821. Now our confidence interval, it's T of alpha over 2 times square root of S squared over N. So now, since we have 0.01, now we have to divide that by 2. We still have 9 degrees of freedom. So our T of alpha over 2 is equal to 3.25. So therefore, we have negative 0.2 plus or minus 3.25 times the square root of 4.4, our S squared, divided by 10. I will put that into the calculator right now. Negative 0.2. We have plus 3.25 times the square root of 4.4 over 10. So we'll call that 1.956. And now the other end, we change that to a minus, negative 2.356. Oh, that's a goofy 5. So if you wanted to use the confidence interval approach, 0 is well within that interval. It's nearly the middle of it, so you wouldn't reject. This 2.821 is our critical value for the hypothesis test. Since this is one-tailed, as you'll recall from up here, it's the t-score that satisfies alpha is equal to p, t being less than the critical. So we look for 0.01, 9 degrees of freedom, 2.821 satisfies that. The reason why we changed to 3.25 for the confidence interval is because the confidence interval goes in both directions. Confidence interval is always two-tailed. Okay, I know it's a lot of work. Does anyone have any questions about the work you have to do before we go to the practice one? Okay, I'll give you about 5 minutes to do the practice one, or 3 to 5 minutes. Same concept as before. You'll just do the work on your own. So I'll give you a few minutes to work on this. Web work. I wouldn't do something this tedious on the test. The reason why is because usually you can have a computer compute the differences for you. So for example, what you could do is you could use Excel, have it compute the differences, average those together, it'll compute the sample standard deviation for you. Sure, there you go. It's on the web work, which is why I'm going over it. Same approach on the test though. The hypothesis test always follow the same formatting. State our hypotheses, state the value of alpha, get your test statistic. If needed, get your p-value and state your conclusion. The rest of the formatting is the same. We're going back and forth, we're playing ping pong. Okay, I'm gonna go back down. If you didn't get it, then you'll need to look afterwards. All right, give you about 3 minutes to work on this. It's a bit of work that you have to do. Pardon? I can't hear what you're saying. Oh, zoom in, yes. Which part needs zooming in on? The data? Okay. Maybe. Oh, dang it. I recommend you write down the data. When you have the data written down, let me know, and then I'll scroll back down. Because when you've written down the data in front of you, it's less likely you accidentally make a mistake. Do you have the data set written down? I will zoom back out so you can see everything. I wish there was a halfway zoom point between the two. I would make this bigger, but then there's not enough space to work through all of it. I'll give you a couple more minutes to work on it. Also, just a fun fact. This is why you don't do small sample sizes, or your t-score has to be very prohibitively large. All right, what I'm going to do here, even if you haven't finished the hypothesis test, that's okay. What I'll do is we'll compute the D bar and the S squared, and then I'll give you a minute or two to do the hypothesis test. So let us zoom in and go back to our tiny ass font size. So we have to keep the differences. It's test A minus test B, 0, -1, 1. Let me go give a bit more space. -3, 3, 1, -1, -2, 2, and 1. Pretty sure you can do this in your head, but we'll use a calculator anyways. Newsflash, you're not going to be rejecting. you have a difference that tiny, then you're not rejecting. So that's our D bar. Now, let's build the table. And then after we get our S squared, I'll stop for a moment so you can keep going in case you had the wrong values. So we have 0, -1, 1, -3, 3, 1, and -1, -2, 2, and 1. Sometimes it can help if you sort them so you can see which ones are duplicates. You can save yourself some time. So we have DI minus D bar squared. The D bar is now positive, so we're not going to have the positive signs this time. So we have 0 minus 0.1 squared, -1 minus 0.1 squared. I'm just going to write this down. That's a parenthesis. Let me fix that. Okay, let me draw the equal signs. This is the most tedious part. It's always the most tedious part of this class, whether it was in chapter 3 or now, it's always the most tedious part. Some other concepts might be harder, but this one's the most tedious. So 0 minus 0.1, square that, 0.01, we only have 1 0. -1 minus 0.1, square that, 1.21, and a little bit of time save, we have a -1 down here, which I believe is this equal sign. Now we deal with the ones, we have a lot of those, which is nice, save a bit of time. On the previous one, we had our D bar was negative, so minus a negative makes it positive. Whereas this time, we have the positive D bar, so minus a positive means we just are left with minus. So 0.81, and we have a couple of extra ones. I missed the 1 right here. 1 minus 0.1 squared. Let's just write it right here. Who cares? Or I can drag this down a little bit. Let's do that. So that was 0.81. And we have it at the end as well. Repeated differences are always nice because it saves time. Now we have the -3 minus the 0.1, so 9.61. Oh, now we have the 3. So 8.41. We are almost there. This is the hardest part, at least the most tedious. That one's 4.41. And 2 minus 0.1. So 3.61. Add them all up. 0.01. Let me just add them all. I'm not going to blabber. $30.9. That should be a 0, not a 6. We have to divide this by n minus 1. If you divide by 10, you screwed up. So 10 minus 1. Come on, calculator. And divide that by 9. Now we have a bunch of decimals. When you actually start doing the test, don't forget your decimals because of rounding. So that'll be 3.43 with the 3 repeating. All right, now I'll stop for a minute. Let's do the hypothesis test now that you have all your data. The hypothesis test for these is actually pretty easy. Just actually getting your D bar and your S squared is the most annoying part. So I'll give you a minute to do the hypothesis test. Imagine if we did a third example like this. You want to go jump out the window at that point. This is why you only have one of these on the actual web work. If I gave you more than one of these, that's sadism. And you'd spend more time on those 2 problems than everything else combined. I'll give you one more minute. You can see when they say you may wish to use software, this is why. It's really tedious, really fast. This is why this is on the web work and not on the exam. This was on the exam, that'd be too mean. All right, I'm gonna go over the answers. It's okay if you're not done, that's fine. As long as you understand the concepts, that's what matters the most. So let's get, it's on the web work, yes, not the exam though. So here we're trying to see better if they do second on first. That means the difference is negative. So like before, mu d is less than 0. It's therefore otherwise greater than or equal to 0. We already discussed this is matched pairs. Now we need our degrees of freedom. df is equal to 10 minus 1, so 9. And now we go back up. Our t-score, d bar minus mu d over the square root of that. So our test statistic is equal to 0.1 minus 0 over the square root of 3.43 repeating over 10. I'll put this in the Desmos. I am not going to round that at all. So we have the 0.1 minus 0 over the square root of 3.43. I'm just going to sit here and enter 3 until the end of time. So that's fun. Now we have 10. I'll move to the left so you can see it. There we go. Good enough. We can get rid of some of these 3s. Then you can see that. As long as you have enough of them, that matters the most. Either way, our t-score is 0.171. So that's our, now again, this one is now positive. And the interesting part here is we're asking if they do better on the second test, even though differences are positive. So if anything, if this did mean something, it would mean they do better on the first test. So here your t-score is going to be positive, but your critical value is going to be negative. So our critical value, it's one-tailed. So 0.05, we have 9 degrees of freedom. You have to make this negative. So negative 1.833. We're trying to see if they do better on the second and the first. So you saw on the previous one, the test statistic and the critical value both have the same sign. On this one, they're different signs. That's called screwing up your hypotheses, but that's WebWorks' problem, of course. And very clearly, we don't have to write anything out. That's just very obviously not going to reject. Now our 95% interval, 0.1 plus or minus our t of alpha over 2. We have to divide the 0.05 by 2. So now we have 0.025. So now we're doing with 2.262 times square root of s squared over n. So square root of 3.43 blah, 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 blah over 10. We'll get the positive end of that. So 0.1 plus 2. It was 1.833, I think. Let me check. 2.262, I was right the first time. Uh, 3.4, I'll just add like 10 threes, that's good enough. There we go, so the upper end is 1.425. And our lower end, we just switch this to a minus. It's negative 1.225. Very clearly, 0 is right about in the middle of there. So on the confidence interval, you would not reject. The tediousness is done. Let's move on to our last bit of material for the entire semester. 2-sample t-test. This one, the shortcut that I use, you have one test taking 2 different people. So think this way. Imagine if you took an IQ test and then your friend takes the same IQ test. Now, this thing that as one test taking two different people. Or if you have a machine and you want to see how good the machine is around people, you could have one worker test the machine, have a different worker test the machine. So the test has two different people taking it. And it's not matched pairs because we have one test. So the easy way is matched pairs, one person, two tests, two sample T, one test, two people. Another way you could think about it, let's say you're testing water levels in the lake to see if it's uniform across the lake as gravity might suggest. You could take it from one side of the lake and then the other side. The test is the water level. You took it at different points. So here this means we have two samples. The degrees of freedom no longer -1, it's -2. You might say, why? Where'd the -1 go? You're changing numbers on this. It's no fun. The reason why is because each sample has n-1. So if we have a sample of 50 and a sample of 100, then they have degrees of freedom of 49 and 99. So it would naturally be reasonable to assume that the degrees of freedom of both is the combination of their two component degrees of freedom. Now, again, we deal with s squared, not the square root of s, because the formula has s squared anyway, save us some time. Now, I know this looks a little bit goofy. This is actually just pooling your standard deviations. Now, something to keep in mind, we are assuming that the population variances are the same. If they're not the same, then the samples are already different. So, I mean, you can test for that. But for us, we're more so concerned about the means, and using the population variances being equal not only gives prettier formulas, but also is actually more restrictive. If you use unequal variance, you'll have slightly different t-score and z-scores. As a practical matter, if the two samples are the same, i.e. they came from the same population, it would naturally follow they have to have the same variance. And most of the time we're checking to see whether or not they came from the same population. So this is a bit of a simplifying assumption. If you're interested in unequal variances, you can check the textbook, but the formula for degrees of freedom is the nastiest thing you will see, even nastier than hypergeometric. If you don't believe me, go look it up, and you'll be very glad we're not worried. We will usually cover two-tailed here. And again, this, technically you've already seen this before from the previous chapter. And the test statistic is very similar formatting to when we were dealing with the p-bar, with the two p's. The difference of the two samples of the square root of their variance, then the n1 over, and then one in the end. So I'll give you a moment to write this down. Then we'll go over our two examples, and then we are done for the semester. Okay. Does anyone need some extra time to take a picture or take a snip of this? What I recommend you do if you're writing these down, write down the formulas, because that's what we use for the problems, and you can write down like the qualifiers that allow you to use it after class or something. Okay, let's go to an example. A little bit to the left so we can see it. We have two apparently very egoistical teachers who thinks one is better than the other one. Same final. The students, they're taking the same test. The only thing is you have two classes taking the same test. That's our indicator that this is two sample T instead of matched pairs. Now you'll notice this value of alpha is not in your T table. I'm going to give you a website that you can use to deal with values of alpha besides the standard ones. We'll get to that in a moment. First of all, we need our degrees of freedom in our S squared. You need degrees of freedom for S squared. So our degrees of freedom is equal to 41 plus 40 minus 2, which is 79. And now our S squared, we have N1. You might say, why is it N1 minus 1 and not N1? Because our sample size is N. Should we be weighting by N? You'll recall our standard deviation formula, we were dividing by N minus 1. So we have to multiply by N minus 1 to clear that out. So this is why we have the N1 minus 1 instead of just N1. Either way, we have 41 minus 1. The standard deviation of the first class was 17.1. So 17.1 squared. Let's do over just a little bit to give some more space. And then plus, now we have 40 minus 1 times 18 squared. And now we divide by our degrees of freedom, 79. So I will put this into Desmos. Recall which order it was. I think it was 40 and then 41. Oh, wrong way. You didn't see that. And then we had 17.1 and then 18. And now we have 79. Our variance is 308.005. We can stop it there because it's nothing but tiny numbers after that because we literally have a 0 right afterwards. So 308.005. Now we can get our t-score. So our t is x1 bar, so 83.4 minus 77.4 over the square root of this. I'm just going to draw the arrow to save a bit of writing. Then we have 1 over 41 plus 1 over 40. That difference is going to be 6. So I can just put 6 over square root 308.00506.329. Wow, I'm just including the whole thing, so we have no rounding issues. 1 over 41 plus 1 over 40. As a note on the exam, if you're plus or minus point, say 002 or something, that's clearly rounding. You're probably fine. At most, you'd lose 1 point for that. Regardless, that's our t-score, 1.282. Now we actually need to get our hypotheses because we hadn't stated those yet. So now we want to see if they're different. So we can say that mu1 is equal to mu2 is our null. And our alternative is that mu1 is not equal to mu2. Now here, again, you can do the alpha either. You can do alpha over 2 and then compare it to p-value, or you can double the p-value. Both those will work. But regardless, the test statistic we already calculated was 1.282. Now we need to get our region. For the region, we have to go from alpha over 2 on both ways, because as you recall, if we're dealing with two-tailed, it's the critical value of alpha over 2. In this case, 0.075 over 2 is 0.0375. It's equal to p, t is less than the critical. Now here, the website I was talking about is right here. I believe it's right here. Yes, it is. The link's at the top. It's also on the paint as well, if you need that. Now here are degrees of freedom. We have 79. And the nice thing is here, the two-tailed will do it for you. So if you wanted to, you can just literally put in 0.075 and it gives you your t-score. On the other hand, you can do the 0.0375, and I probably inputted that in wrong, but whatever. Go with the 0.075. 1.804. Oh, it just flipped them, that's all. 1.804. Right? Two-tailed, yes. 1.804. So, negative infinity to negative 1.804, and then 1.804 to infinity. If our t-score is in here, this should be a decimal. If our t-score is inside, oh, I didn't write that down correctly. Sorry, we have to use the union. With the union of 1.804 to infinity. Either way, t-score of 1.282 does not fall into that range, so we do not reject. You never reject nor fail to reject the alternative. We're always dealing with the null. So if you see something that says reject H1 or don't reject H1, instantly wrong. Although to be fair, you have unlimited attempts, so I suppose you could guess your way through that. Now, let's suppose we wanted to convert that t-score to a p-value. Well, then we'd have a t-score of 1.282. You can go to this website to get your p-value, so 1.282. And our degrees of freedom was 79. It doesn't matter what your significance level is. We're dealing with two-tailed. Come on. And so there you can see that p-value is nowhere close. And don't worry about assuming that p is less than 0.05, because in this case, it'd be p is less than 0.075. So if you want to get the p-value and use the p-value approach, you can use this link. If you want to use the critical value approach, you can use this one. Both of them work. You're probably going to want to write this one down for the practice one. So I'll give you a second if you want to write it down or take a picture, because you'll want this one for the practice. All right. Let's go to the practice one. This is your last practice problem of the semester. I'll give you a couple minutes to do this. And I have the links right here in case you couldn't get them written down. You'll notice the alpha is the same. So if you wrote down the t stuff from before, you just saved yourself some time. Some of you are not going to have 0.075. Some of you are going to have the nice pretty ones. Some of you might have the ugly ones. I'm hoping that for the summer and onwards, we just stay with pretty ones only. Talking with the webwork guy to get that sorted out. So hopefully anyone watching this from the summer onwards gets the pretty numbers. It doesn't have to worry about the links. Yes. Pardon? I'm not going to answer that question for this one. Because this one, the work's not tedious. I can't say you're not going to have tedious work on the test. If you want the best preparation possible for the test, take the practice one. That practice one's going to be 90+% similar. Yes. Oh, okay. Many of you thought that the new practice assessment number 2 was pretty similar to the other one. This one's nearly identical. The only thing that changes the numbers in the background. Other than that, everything else is going to be pretty much the same. I'll give you one more minute, and we'll go over it. And then we are done for the semester. Although I suppose if you're watching this as chapter 10 before chapter 14, then you'd have one more. But for all of you in person, you're watching it in the right order. Keep in mind, you'll have 90 minutes on the midterm exam number 2. I'd be very surprised if you need the full 90. You could probably finish in 60 or less. All right, let's go over the answers. So first of all, our degrees of freedom is 49 plus 40 minus 2, which is 87. Now we need our S squared, which is 49 minus 1 times 17.9 squared plus 40 minus 1. Go a little to the right to get some space. Make that more clear. Times 18.9 squared. Now we divide that by 87. So I will put this into, oh, come on, out of the way. Shoot, go away. There we go. So we have 49 minus 1. I think it was 17.9 squared. And then 40 minus 1 times 18.9 squared over 87. Let me double check. 87. All right. 336.907. Now we are ready to go. Our t-score is the difference of the two x bars over the square root of s squared times 1 over n1 plus 1 over n2. So our t is 85 minus 80.4 over the square root of this times 1 over 49 plus 1 over 40. So that is going to be 4.6. Square root 6.906. I'm just going to type in the whole thing so we don't have to worry about rounding. Times 1 over 49 plus 1 over 40, 1.176. Let's go ahead and state our hypotheses as well. Once again, we're trying to see if they're different, so the null is there the same. So we'll say mu1 is equal to mu2. If you want to, you can write down mu1 minus mu2 equals 0. That is correct as well. On the exam, I'll tell you what formatting to use. So on the exam, it'll state the signs in them and you'll state the values. And then here we have mu1 is not equal to mu2. Our test statistic we already got, 1.176. Since our alpha is the same, our rejection region is going to be the same as the previous one. So from before, we had negative 1.804. And then the U for union, 1.804 to infinity. Now they want the p-value. So we have 1.176. So 1.176, and our degrees of freedom, I believe, were 87. Significance level doesn't matter. It's two-tailed though, so they'll double the p-value for us, 0.243. Oh, what was that, 283 or 243? 243. And I will draw an arrow so you know where that came from. Therefore, we do not reject, because the p-value is obviously not below the alpha, and our critical value is not inside the union of those two ranges either, so we don't reject. That is our last example. Are there any questions about literally anything? Because if it's not, then for those of you who are at home, then we are done. All right, those of you at home, enjoy the rest of the semester and best of luck on your web work and your... Yes, there's a practice. It is on Blackboard in the practice assessments and exams folder. All right, those of you at home, enjoy the rest of your evening.